So we looked at deductive proofs and identity proofs, but could we also prove things in other ways? Does this prove that a squared plus b squared equals c squared? Do you see it? Because here we have this triangle A, B, and C. And it's repeated four times. So because I have four triangles here and the same four triangles here, A, B, A, B, A, B, A, B, does that prove that A squared, right, if I color in everything but the triangles, there's my A squared, there's my B squared, and if I color in this part, does it make sense that the colored parts have to be the same? Is this good enough to prove A squared plus B squared equals C squared? No? You don't think so? You need algebra? I don't know. I think it kind of proves it. What's wrong? Would you not say that these two squares are exactly the same? Like, this is A plus B, this is A plus B. The big squares have to be the same because I'm using A and B on both of them. This has to be a square because it's A times A. This has to be a square because it's B times B. Does this have to be a square? Well, if that's 90, would you agree that this angle and this angle add up to 90? And then this angle is the same as that one over there. So since these two add up to 90, that green one is 90 degrees. Then if you X out 4 triangles here and X out 4 triangles here, what's left have to be equal. And so the area here, A squared plus B squared, has to equal C squared. But it's a different way of doing a proof, right? You could also just use this as algebra, okay? You could use, if you wanted to do a proof and just use that as algebra. What is the area of the whole thing? It would be a square, which is A plus B times A plus B. It's also, I could figure out the area of the whole thing by doing the C squared plus 4 triangles, and each of these triangles length times width divided by 2. That would be just using the right-hand side and thinking about, I could count the area as one big square, A plus B times A plus B, or I could think of the area as the C squared plus 4 triangles. Now, if I simplify this, I'm going to get A squared plus 2AB plus B squared. If I simplify this side, I'm going to get C squared plus 2AB. Does this prove that A squared plus B squared equals C squared? Well, I could subtract 2AB on both sides, and I'd have my proof. So it's showing that we can sometimes have proofs in different ways other than algebra. Okay? I think another beautiful proof is the following. What have I shaded? I shaded a quarter of the square plus a quarter of a quarter, a 16th of the square, plus a 64th, plus, and if I did that forever, this would make an infinite geometric sequence. But without using the formula, because you have a formula, S infinity on your formula sheet, U1 over 1 minus R, without the formula, I can tell right away from the picture the answer is 1/3. How do I see it in the picture? Well, of the big squares, how many are shaded? 1 out of 3. Of the next size square, how many are shaded? 1 out of 3. 1 out of 3. 1 out of 3. If I did that forever, I'd always have 1 square shaded and 2 unshaded of each and every side. And if that added up to the whole thing, it means that the shaded area in total has to be 1/3. It's a beautiful diagram proof. But we're not used to diagram proofs so much. We're more used to like, oh, we have to use algebra. That's more proper. Okay. Logic proofs. I like this. A set of cards has a number on one side and a letter on the other side. Tim claims there is a vowel on one side, there must be an even number on the other side. Which of the following cards must be turned over to test that? And they actually did this as a psychological study. So you can flip over one card and be certain that this is true. Or which of the following cards? Which ones? You might have to turn over more than one. Okay? Very few people give the correct answer for this. Okay? Now, read this one. 4 people are drinking in a restaurant bar. If someone is drinking beer or any other alcoholic beverage, they must be over the age of 18. Correct? Okay? Which of the following people need to be investigated? Would the waitress go up to the Coke drinker and say, I need to see your license? Would they check the 16-year-old at this point? They're just 16. They're not doing anything right now. Would they have to check the 28-year-old? No. Would they have to check the beer drinker? How old are you? Yes. That's the only one they'd have to check here. Because right now, this is what you know. You just know that that person's 16. You walk into a place and you're 16, they don't jump on you right away and say, I need to see your license. But if you ordered an alcoholic drink, then they would. But they definitely need to check the age of the beer drink. Was this hard to figure out compared to the last one? And what's interesting is that these 2 questions are exactly the same. In this one, the only one you have to find out to test is if there's a vowel on one side, there must be an even number on the other side. You'd have to check this one. Because working vice versa, these don't matter. But we take it out of context, and our brain is unable to solve it. And we put it into a context we're familiar with, all of a sudden our brain is able to solve it. So it's interesting logic and proofs in logic that way. Oh, we're gonna have fun today? Okay. Problem-solving strategies. You have developed problem-solving strategies all the way through your mathematical career. You use them all the time, right? Would it be good to understand the problem? Yes, that makes sense. Okay, make a plan. Carry out your plan. See if it works. Reflect on your results. So these are just like, hey, try this. See if it works. In fact, I have his books somewhere over here. Of course I can't find them anymore. But he wrote 2 famous books on problem solving. I'll find them later. Okay. Also developed a set of problem solving strategies called heuristics. Here's one that you've probably done, right? If it's hard to solve a difficult problem, try solving an easier one, right? For example, my grade 10s, I said, what is the following equal to? And they got stuck because they didn't remember the exponent rule. But I said, okay, what would you do if the numbers were easier? Oh, this means 2 x's, this means 3 x's. You add them. And they remember the rule when it's easier. And then they can apply the rule in a more difficult situation. Okay. Look at it quickly. Say the answer that first comes to your mind. It's probably wrong. Double check it and then see if you can figure it out. That's actually a good problem-solving strategy. Getting a wrong answer and checking it. What's the first answer you wanted to say? $1.10? How many people came up with that? It doesn't work. Bottle and a cork cost $1.10. The bottle is $1 more than the cork. So, do you see your brain wanting to do $1.10? But then it's not $1 more. What would the right answer be? $1.05 and 5 cents. Okay? Could you solve this with algebra? Yeah, you could say, let the cork cost X, and the bottle would be 1 plus X. That together equals $1.10, and you could solve this. Right? This would be algebra saying that 2x, move the 1 over, is 0.1. So X would have to be 5 cents. So we can use our algebra as a technique to solve something. But this is a great example because your brain will naturally just go to $1.10 right away. Because it just seems like, oh, that's so easy to do. One of them is $1, there's the difference of $1, and then 10 cents. To misread the question. Okay. We're going to put you into groups by row. Group 1, Group 2, Group 3, Group 4, Group 5. You're going to try to solve this. Grab a whiteboard somewhere and solve this problem.